Did you come up with the same thing I did? Sodium sulfate. Sodium's a +1 ion, sulfate's a -2, so it's Na2SO4 solid. So we need 2 sodiums, 1 sulfur, and 2 diatomic oxygen gas. And delta H0 sub F is negative 1384.5 kilojoules per mole. Nitric acid liquid, nitric acid is HNO3 liquid. We know the delta H0 sub F is negative 173.2 kilojoules per mole. So we need a half a mole of hydrogen diatomic gas, half a mole of nitrogen diatomic gas, and 1.5 or 3/2 moles of oxygen gas. So hopefully if you think of it as starting with the product, it won't seem as difficult to try and balance this with the fractions, because you can just look at it and say, well, I need 3 of these and they come in pairs, so I need 1.5. And you're kind of building your reaction one step at a time instead of trying to balance something that's already written. So being able to write thermochemical equations for a formation is a skill that's an objective of this class. So when you see on the test, write the thermochemical equation for the formation of whatever compound I dream up, you will have a chart with enthalpy information on it, so just do what we just practiced. Now, sometimes we like to put things in multiple choice format and say, identify, does this meet the criteria? So let's look on the next page. You look at these equations and tell me, do these meet the criteria for standard enthalpy of formation reactions? Do they meet the criteria? How about the first one? Yes, we have a balanced equation with subscripts. It makes 1 mole of product and all the elements, all the reactants or elements in their natural state. How about the second one? No, why not? We have 2 moles of product, so that doesn't meet the criteria. How about the third one? Why not? This is not an element in its natural state. And how about the fourth one? No, why not? Hydrogen and oxygen are monoatomic in this, and it's got to be diatomic in its natural state. So that's how we prepare thermochemical equations. Formation. Was there a question, or you're good now? Okay. All right. Any questions on how to write those equations or how to recognize them? Okay. What do we do with enthalpies of formation? We can use tabulated data about enthalpies of formation to perform calculations about enthalpies of reaction. We looked at Hess's law. That was one way to calculate the energy change in a reaction. Using standard enthalpies of formation is another way. We know that anytime we have a change, it's products minus reactants. So for us in chemistry, well, it's final minus initial. So for us in chemistry, a change in enthalpy is the change in the enthalpy of formation of products minus the enthalpy of formation of the reactants. So we'll look at a problem where we are calculating the standard enthalpy change using tabulated data. So the first thing that we would do is check to make sure the equation is balanced. Always check that first. I have it second here. This one is balanced, so we're good. Then grab your chart or table and look up the enthalpy of formation for everything listed. So I did this. Sodium hydrogen carbonate is negative 947.7. These all have units of kilojoules per mole. The sodium carbonate, negative 1131. Water liquid, negative 285.9. Be careful about water, because when you look up water in the tables, there's water liquid and water gas. Make sure you get the right one. And then carbon dioxide gas is negative 393.5. They all have units of kilojoules per mole. Now, if the coefficient in the balanced equation is not 1, we multiply the number on the chart by that coefficient. Well, even if it is 1, we're multiplying it by 1. Then we add the products because it's always final minus initial. The enthalpies of the products minus the enthalpies of the reactants. So for this one, the standard enthalpy change for this reaction will be equal to the products. It'll be the enthalpy, the standard enthalpy of formation for sodium carbonate, one of the products, plus the standard enthalpy of formation for water liquid, plus the standard enthalpy of formation for carbon dioxide, minus 2 times the standard enthalpy for sodium hydrogen carbonate. And I'm multiplying 1 times all of these. I just didn't write it down. So we go ahead, look at these numbers, and we can now stick the numbers in. We know the standard enthalpy of reaction is equal to 1 mole of sodium carbonate times negative 1131 kilojoules per mole plus 1 mole of hydrogen times, or water, not hydrogen, times negative 285.9 kilojoules per mole plus 1 mole of CO2 times negative 393.5 kilojoules per mole. Now I've added in all my products. Now I'm going to subtract my reactants. Minus 2 moles of sodium hydrogen carbonate times negative 947.7 kilojoules per mole. So we add in the products, we subtract out the reactants. Now we just have to go through and add them all up. So delta H0 for my reaction is equal to negative 1131 kilojoules, the moles cancel, plus a negative, so minus 285.9 kilojoules, minus 393.5 kilojoules, plus 1895.4 kilojoules. Now, I take time to write all this out because it makes it easier for me to keep track of sig figs when I'm adding, because now I can look at where my last place of significance is. So when I add these all up, delta H0 for this reaction is equal to 85 kilojoules. I stop in the ones place, so I end up with fewer sig figs because of addition rules. So you add in the products, you subtract out the reactants. Sometimes my students like to add up all the products, add up all the reactants, and then subtract. That's fine. Mathematically, it's the same. The only thing you really have to watch is you're adding and subtracting. Some of the numbers are positive, some of them are negative. Make sure you don't slip a sign. Okay, the next one I'd like you to do with your groups. How many of you have your books? Not that many. Okay, so go ahead and